Hello, Narnach here. Welcome back to TIS-100. One of the viewers asked in the comments to basically show the process of solving the problem rather than explaining my solutions after the fact, because there is a difference between coming up with the solution and actually just explaining it afterwards. So I'm going to attempt that with the Signal Pattern Detector. I haven't actually solved this one yet. I've just been staring at the problem description for a bit. So here it goes. So, the Signal Pattern Detector. We read a value from in, that's up here. And we look for the pattern 0, 0, 0. And we write a 1 when a pattern is found, and if that's not so, then we write a 0 instead. That we write it out here. So we have to connect these nodes down here. This is going to be the shortest path. If we can do it in 4 nodes, these 4 nodes are going to be it. So if we go back for a second to the interrupt handler, which was the previous solution, we had a similar thing here as well, but here we're looking for a change in pattern from a 0 to a 1, and based on that we make something happen. And the solution I used was a state machine. So I just keep the node in a state and transition until we reach the state where we actually have to emit a value rather than nothing. So I'm gonna look if that same solution is going to work. So we're just going to start up here, write as much of the solution as possible, and then see if we can treat the bottom of this as a dump pipe and then later optimize it. So we start with moving up to the accumulator. We probably want to wrap this in a main function because there will be iteration. So we will be looking for a sequence of 3 zeros. And whenever we don't find a 0, we go back to main. So we also know that if we are in the main sequence, we haven't yet achieved a success. So we can just move 0 down, because we always emit a 0 until we have 1, 2, 3 zeros in a row that allows us to emit the 1. So if we're in the main, that means we haven't achieved our goal yet, so we can emit a 0 without even looking at the value. And that's useful because then we always do this, and then we don't have to conditionally do things in other locations. So chances are that, let's see, we have 3 different things. We can see if the number is smaller than 0, larger than 0, or equal to 0. And equal to 0 is the one thing that we care about. Even though if you look at the input values, they're all positive. So in this case, if it's greater than 0, we can jump back to main. That way we have a straight up jump for, oh, we still need to move up to the accumulator. So this basically, if I do the jump to equal to 0, I'm following the exact description of the puzzle, because there's all positive numbers. I'm using that fact to choose how to jump. And because if I do a jump equal to 0, that means we can advance to the first one found. So basically we would have first stage, 2, 3. And in case of the 3, we do move 1. And here, and it's already starting to look like it's going to be very, very, very cramped. Okay, I'm doing part of this in my head, and part of this I'm explaining. I'm jumping a bit ad hoc. So that's also one of the reasons why I have focused mostly on just explaining solutions after the fact, because the process of coming up with a solution it's rather messy. It's it's part systematic, it's part just chaotic. You get flashes of inspiration, you follow certain paths in your head, and then you just jump back, and at some point it clicks. Sorry. So, let's see, at this point we have 0 successes. So we emit a failure. Then we actually look at the value. We also need to jump back to main. So if it's not equal to 0, we reiterate back. So in this way, yeah. So we emit the 0. Maybe it's more appropriate actually to do it this way. So first we read a value and then we emit something. So that way we will not be emitting values before we have even looked at the values. Even though technically we could do it, because we know in this state we're never going to emit a 1. But let's keep it clean. So this way we can do a move up to ACK. And then once again, if it's equal to 0, we move to 2. Otherwise, we jump back to main. Wait. Okay, so I'm already starting to run out of space. I could just compress this by taking this one out. And basically using relative offsets. That helps me get back to main. Problem is, jump equals to 0, the value-based jumps. They always take a label rather than a relative offset. Just double checking. It's always a label, yeah. So I can't use a number for that, which kind of makes it really hard to abstract away all the other jumps. So basically all we would do is just get one label out. So their space is just not going to be there. Okay, so we have too much space, but I'm just working through this, I'm spotting a pattern. We don't really care about the value. All we care about if it's 0 or not. So because this solution, it has multiple stages. One of them is reading the input and analyzing if it's a 0 or not. The second part is keeping count. How many zeros have there been in sequence? So anytime there's a 0, we increase the sequence. Anytime it's not a 0, we reset the sequence. And as long as the sequence count is greater than 3, we emit a 1. If it's not, we emit a 0. So that's part of the insight I've got out about the problem and how to potentially solve it. So we can break it apart, because we don't have enough space to do everything in a single node. That works for the simpler puzzles in the beginning, but here not. So we need to decompose it. So this one, it's going to be a main function, and all we do is we move the value to ACK. If it's equal to 0, it's 0, and otherwise it's not a 0. So So now we take the inputs, and as before I was slowly going towards a path where I looked at the inputs and I was like, hey, all I see is zeros and positive numbers. I don't see negative numbers. Maybe we could use the JEZ, so the jump if greater than zeros instruction, to make my main loop a bit more optimized. that was, I was making assumptions there that based on the data of the first test set was true. Based on the description of the puzzle, it was not true. I was taking a shortcut that I had no right to do, but it might just work in practice to get a better score. By decomposing it and basically just ensuring that I format my own data, I can make that assumption. So now, if we have a 0, we emit a 0 down, and otherwise we emit a 1. So here we either get a 0 or we get a 1. There's no other values anymore. So we can use that to our advantage. So here we can actually start counting. And actually, rather than emitting 0s and 1s, we can probably do a relative offset to control a loop here. So yeah, so the purpose of this node is basically to keep a counter of zeros, and we emit the value, the total down. So here, every tick we get, we receive a count, and then if the count is greater, well, if count minus 3 is not smaller than 0, then we have a sequence. If it's not completely clear, it will probably become clear once I start coding it and explaining it a bit further. This is at least the current tangent I'm going off on. So we have the counter of zeros. So we are going to use relative offsets, and we do that because that way we can. Because if we just take the raw value of 0 and 1 in, we need to do a move up to ACK. Then we need to analyze ACK, so that's going to be a jump based on ACK. And then we need to use buck to store the data, and that's a lot of swapping of data. That's probably not going to be very efficient. So if we use relative offsets, then we can use the direct value that's emitted by the top node, and we don't need to store it in ACK, so we can just keep a counter in ACK, and that's going to be a pure one. So let's say we have a main loop for now. Let's call it main. So first what we do is we jump relative offset based on up. So we read the value. If there is, let's see, so there's two situations that can happen, and I'm going to label them for now. So we get a 0 or we get a 1. If we have a 0, we add 1 to ACK, and then we let's see, let's add another one called flush, which moves ACK down. So that's going to be a jumper flush. If we have value of 1, that means it's not a 0, which means we need to reset. So that's we reset it by putting the value 0 into ACK, and flush needs to be a label. So what happens? Main loop. We do a relative offset based on the value of up. So if we have a value of 0 up here, let's see, we need to do a jump one instruction now. So we go from here to here, that's +1. Then we add 1 value to the accumulator, so the 0 count goes up by 1. And after that we jump over to flush, basically to not execute the code that's meant for the instruction that triggers when we get a value of 1 rather than 0. So we jump over to move to flush, which just flushes the ACK value down, or so it emits the value So here we can act based on the current counter value. If we have a value of 1, we need to, let's see, from here, 1 instruction, 2 instructions, 3 instructions. So here this is going to be 3. So then we clear the buffer, and then we automatically fall through to this instruction, to the flush instruction, and we emit the value once again. So here we clean up our input to make sure we only get zeros and ones. Here we count the occurrence of the number of zeros. So here we need to actually do something with it. And let's see. So what we do is we move the up value to ACK. Then we do a subtract of 3. So let's sketch out our boundary conditions. So if the value is 3, let's see, everything below 3 doesn't make it doesn't trigger. So 0, 1, 2, that means we emit a value of 0. If it's 3, we emit a 1. If it's 4, we emit a 1. So what I'm thinking, and what I was saying before, we take the value and we subtract 3. If we have 3 minus 3, that becomes a 0. If we have 4 minus 3, that becomes 1. Both. So this is a 0 value. This is a positive value. If we take 2, or any number below, if we take 2 and we subtract 3, it becomes minus 1, so it becomes negative. So negative numbers as an input result in a 0. All other values, whether they are 3 or higher, they result in a 1. So if you subtract 3, then jump, if it's less than 0, to emit a 0. And otherwise, we move a 1 to the right. And then we need to wrap a loop around it again. Because we jump back to main. Move 0 to the right, and it will automatically fall through. And here what we do is we move the value from the left and we move it down. And let's see. And it actually just works out of the box. And if you look at the value, the input values, they're all still positive. So my assumption actually did hold, even though I'm sanitizing the input. I shouldn't have, because the data is all positive. And this is the thing with this being an abstract puzzle. All you have is a description. You don't have any real world context to anchor your expectations in. For example, if the list of inputs, if they are, I don't know, a series of time durations of how long, I don't know, sprinting runs took or something. You know, if you're running something, you can't run for a negative amount of time unless you are able to walk backwards in time. So then you can anchor your expectations in reality to know that, okay, this number is never going to be 0, so I can use that in my solution. In this case, I decided not to rely on it. So we have 219 cycles. We have 4 nodes and 17 instructions. So it's interesting that I'm falling slightly on the slower side of a big hump of popular solutions. So I could probably take another 10 or 20 cycles off to get it into the solution that a lot of people took. Not a lot of people had this exact solution. And also 4 is the lowest amount you can possibly go. So of course I'm in the top of that one. But usually if there's a bump with more nodes, that means people used more nodes. And instructions 17, so people got as low as 12 or 13. I'm not quite sure which side of the boundary this is. Okay. So that's a first solution. So let's return to the list. We copy it. And we name this one second. So we had 219/4/17, I think. Yep. So that's the first solution. And now I've run through it, so I have idle percentages. So this node is idle 4% of the time. That means this one is doing most of the work. And it also means that this is actually the blocking factor. This is the bottleneck. So let's see what we can do about it. So let's analyze once again. So we take the value from up and we store it. We subtract 3. And then we jump if it's less than 0, which emits a 0 value to the right. And then we move a 1 to the right, and we jump back to main. But we have a lot of space here. So I'm thinking, what if we inline the main function? So basically this is the one function, so to say. So what if we just take this code and do it like so. So basically if we have so this is where we start again. We read the value, we subtract 3, and we don't have to jump. We don't have to jump. And this is where it gets interesting. So what? I had a diagram up before with the boundary conditions. So if we had 4 minus 3, that's 1. 3 minus 3 is 0. 2 minus 3 is negative 1. The problem is that the success values are in 2 different checks. Because if we want to detect this, we have to use a jump if equal to 0. If we want to detect this, we have a jump if greater than 0. And this we can do with a jump if less than 0. So that's why I chose the solution to go with a jump if less than 0. What if we use a different value? Let's say we subtract 2. 2 minus 2, of course, is 0. And then if we take 1 minus 2, it's negative. Here, 3 minus 2 becomes 1. 4 minus 2 becomes 2. So what I did here is took the success values, and they now both are detectable using the same instruction. So if we do a different comparison here, then for the success case, jump if greater than 0, you can jump to 0 to 1. Otherwise we fall through to 0. And this should work. Okay, so speeding up the solution. 204. And we use 2 extra instructions. So 204. 204/4/19. So this is still the slowest node in the of the bunch. See, it's still 4% idle. So what can we do to make it faster? Because there is a faster solution. Can we do a similar thing here? Rather than subtracting 3, we subtract 2. So if we do a jump if greater than 0, actually, no. This is, I don't think we can optimize this one. Because we already, there are no more pointless jumps in here. All the jumps now have a function. So this is as optimized as we can get it using the current strategy. Wait. Of course, we're doing 2 things here. We are doing 2 things here. We are taking the value, subtracting the value, and then we make a decision based on the value. Subtract, decide. Those are 2 steps. And here we have a node that's doing nothing. So let's once again go here, copy it. So this is the 3rd solution. So if we subtract 2, then all the success cases are going to be greater than 0. So we just move back to the right. Just take that code up. Okay, so we take the value from up, we subtract 2, and we move it to the right. Then we do all the calculations over here. We have a main loop again, move left to ACK, and then we do a jump if greater than 0. Then we, let's see, we need to reverse it. Wait, I'm being stupid. Let's just keep the number there. So then we do a jump if greater than 0 to a 0. No jump if less than 0. Let's see if this still works. It's stuck. What? Oh, this one was still reading the value from up. It needs to move it from the left. It doesn't need to oh wait, of course, we no longer make a distinction, so there is no need to read the value more. So we once again have the interesting problem that we have a jump main here. This should, I was going to say this should work, but it's not. Oh, we're moving to the right. Maybe we should move it down. It's always the thing with moving code around. Forget the, okay, so 204, 418. So we basically got one instruction out, 204, 418, but we are not done yet. Well, if you look at this one, this is now up to idle 23% of the time, rather than 4%, so this is no longer the bottleneck. This one now has an idle percentage of 12, so this is the one that's most busy. And this one still has some inefficiencies that we can have a look at, because we have a jump main, and every time you have a jump main, basically that means you should be able to inline the main function. Wait. We need to have multiple tests. This might not be more efficient. We'll see. So once again, if we inline the main function, we move left to ACK, and then if it's not less, if it's greater than 0, we move to 1. If it's equal to 0, also move back to 1. That's the problem. If we are going to replace one instruction, the JLZ, with its opposite, we need to check both of the variations, and that's probably gonna make it slower, but we'll see. 204, 420. So in terms of speed, it didn't make a difference, but we used extra instructions. So we might as well keep it simple. Because, okay, so this is now 19% and it was 21% idle in a previous solution. So it didn't matter because this was the bottleneck. So we can have a look at here. What are we doing here? We are doing relative offset jumps based on the value of up here. And basically we're counting. That's all we do. We count. Is there a way to improve this? Don't think so. Nothing that at least that obviously springs to mind. People did manage to make it faster. but not by a lot. So this is the point where logical analysis and inspiration are kind of the things that are both equally useful. You can analyze to tiers, but unless you spot the thing you were missing, it's going to be hard to optimize it further. So let's go through it one more time. And we're kind of running late on the time, so let's do this quickly. We move the up value to ACK. We jump if it's equal to 0. In that case, we move a 1 to just move on here. Otherwise, we send a 3 to flush it, and we jump back to the main. We jump back to main. I remember saying something about inlining jumps to main. Because basically, this one we could label other. So we could say, we do this. Let's see, we move the up value to ACK again. Then I think there was a JNZ jump if not 0. Yes, there's a JNZ. So that works. If it's not 0, we loop back. Otherwise we fall through to that one. Let's see if this makes difference. 194. That made a difference. Just tightening up that main loop over there. So that's 10 instructions. I think we were back to 19, weren't we? Yeah. Okay, so this one is once again the bottleneck. 5% idle. It's really busy. It has a jump flush, which seems useful. What if we inline that? Yeah, let's experiment a little bit. So what if we... And also I'm resetting the instruction count, so I need to change the JRO numbers, the numbers that are emitted by the top node. Basically, I can duplicate this code and then we replace this with a jump main, which is something that we could potentially inline, but if it were not for the JROs, so we'll see. So let's see, if we want to, 0 is still a 1. This one, let's see, 1, 2, 3, we need to add 1 because we added an extra instruction. Let's see if this also works, if it actually works. It still runs, okay, fast forward, 192. It's interesting how most of the time, if you want to increase cycle count, you do that by just using more instructions. So you trade efficiencies that way. There are two glaringly not used blocks here, but I'm having issues seeing how this could be used to do things in parallel or to spread out even more work. So I don't see a reason to actually use them. This one is once again the slowest, but I've been going for almost 35 minutes, so I think I'm calling this one over here the final solution for this puzzle. It's not the most efficient one. Could probably get it down to somewhere in the 180 range. And there is also an option to get it down to 16 cycles based on just looking at the graph. So there are opportunities here to improve it. But I think for now, this was a very nice demonstration of how I try to go about solving a puzzle. And it actually worked out in a fairly reasonable time. So if you enjoyed this, this different style of looking at at the puzzle. So not explaining it after the fact, but just solving it more or less in real time. Well, actually solving it in real time. Then please do let me know in the comments. Yeah, I'll see you next time. Bye bye.